Welcome back everyone. In this lecture we will solve this linear recurrence in full generality. So, let me first do some preparations and then we will actually look at the linear recurrences. So, as we noticed some polynomials are naturally appearing in solving linear recurrences. So, let us first look at some polynomials and what is this reflected polynomial. So, let us start with polynomial of the form C of z, which is given to be 1 plus C 1 z plus etcetera plus C d z power d. So, we will be having very special type of polynomial whose constant coefficient is 1, and we assume that the degree of this polynomial is exactly d. That means this C d is indeed non-zero. So, this is a polynomial over complex numbers. So, given this polynomial, we define the reflected polynomial as follows. So, we define this reflected polynomial, which is denoted by C r of z, which is exactly z power d C 1 z power d minus 1 plus etcetera plus C d. Note that C d is non-zero. So, what is the relation between the reflected polynomial and given C of z? So, note that when we take this C r and then substitute 1 divided by z, so we get exactly 1 divided by z power d times 1 plus C 1 z plus etcetera plus C d z power d. So, that means, so this is exactly equal to 1 divided by z power d C of z. So, that means the relations between these two are given by C of z equal to z power d C r of 1 divided by z. So, why this polynomial is important? When we looked at this Fibonacci series, we needed to solve a polynomial of this form 1 minus z minus z square, but we wanted to write this polynomial in this specific form 1 minus alpha z times 1 minus beta z. So, that we can use this geometric series. So, that is the basic idea. Okay. It is easier to use the geometric series for this type of linear polynomial. So, that is why we need to look at the reflected polynomial of the given polynomial. Then if we take the roots of that, then it is easy to see one can get back to the reflected one can get back to the original polynomial with the nice form which is of this form. Okay. So, let us actually do that in the generality. So, like I said, so we have this relation between C of z and the reflected polynomial C r of z, which tells C of z equal to z power d C r of 1 by z. So, now what we do, we just write C r of z as let us say z minus alpha 1 times etcetera times z minus alpha d. So, where alpha 1 etcetera alpha d, they are roots of C r of z. Okay. Of course, counted with multiplicity, counted with multiplicity. Okay. There are exactly d roots. So, now you can see that if we have the C r of z is this, then C of z becomes exactly z power d C r of 1 divided by z, which is exactly given by z power d 1 minus z minus alpha 1 times etcetera 1 minus z minus alpha d. So, by multiplying by z power d, we get exactly 1 minus z alpha 1. So, you can write it as 1 minus alpha 1 z etcetera times 1 minus alpha d z. So, which is the form we are interested in, because it is easy to invert this thing using geometric series. Okay. So, this is the relationship between the given polynomial which has constant coefficient 1 and its reflected polynomial CR of z. So, by solving this polynomial we will be able to rewrite a given polynomial in nice form. So, that is why we were considering this. So, note that in the case of Fibonacci numbers, the CR of z is nothing but z square minus z minus 1. By writing down the roots very explicitly, we can see that this is exactly given by z minus 1 plus root 5 divided by 2 times z minus 1 minus root 5 divided by 2. So, it is golden ratios that appear in the roots. Okay. So, now let me state the main theorem, and of course, I am going to only prove first two statements are equivalent, remaining things I am going to leave it as exercise. So, but it is very important to actually know the statement of the theorem, that is what important. So, let us write it down. So, we are going to consider this linear recurrence of order d for general d. So, for that purpose we will actually write everything in generality. So, we fix this d, which is the order greater than or equal to 1, and then we take some complex numbers C 1 etc. C d with the assumption that C d is non-zero. So, then we are going to set this polynomial C of z, which is the characteristic polynomial of this linear recurrence, which is given by 1 plus C 1 z plus etc. plus C d z power d. So, this we call as the characteristic polynomial of the linear recurrence. So, of course, I need to say what is the linear recurrence that we are actually looking at. So, we will actually write down in a minute. So, note that one can rewrite this C of z as 1 minus alpha 1 z power d 1 times etc. 1 minus alpha k z power d k, where this alpha 1 etc. alpha k are the distinct roots of the reflected polynomial CR of z. So, where this alpha 1 etc. alpha k are the distinct, because we counted here with multiplicity. So, distinct roots of this reflected polynomial CR of z. Okay. So, now given this data we have the following conditions that are equivalent. So, for a counting function or arithmetic function f, which is defined from n to c. So, the following are equivalent. So, what are they? The very first statement which says that we have this linear recurrence of order d. So, linear recurrence of order d. So, this is the general recurrence that we have. For all n greater than or equal to 0, we have that f of n plus d plus c 1 f of n plus d minus 1 plus etc. plus c d f of n is 0. So, this is the recurrence, and recurrence of this form is called linear recurrence of degree d with constant coefficients, which are 1 c 1 etc. c d. So, we have taken it to be very specific, because so whatever coefficient that we can have here, that can be made into 1 by dividing it by that coefficient. So, that is why we can assume without loss of generality that coefficient is just 1. So, now the second statement which says how to solve this recurrence, so which actually uses what is called this generating function. So, the generating function which tells that if we look at this generating function of this counting function f of n, then we have f of z equal to f of n z power n, where n is varying from 0 to infinity. So, this is exactly given by a polynomial p of z divided by c of z. So, c of z that is already given here. So, this is our c of z. So, here this p of z will be existence of a polynomial p of z. So, that has a degree less than d. So, where p of z is a polynomial in C z with degree strictly less than d or less than or equal to d minus 1. So, if we have a function that satisfies this linear recurrence, then it must satisfy this generating function constraint. That means, the generating function of that is a rational function whose numerator and denominator have constraint. The numerator must have degree strictly less than d, and the denominator must be given by this characteristic polynomial of this linear recurrence. So, that is what it says. So, now this third statement, which actually tells us how to solve this this equation further. So, this equation again can be solved further using what is called the method of partial fractions. So, the partial fractions guarantee that one can rewrite this constraint as follows. So, you take this f of z, which is given by f of n z power n, where n is varying from 0 to infinity, which you can rewrite as summation g I of z divided by 1 minus alpha a z power d I, where I ranging from 1 to k. Note that there are k distinct roots for this characteristic polynomial, and this alpha 1 etcetera alpha k, they are the distinct roots of this reflected characteristic polynomial of that linear recurrence that we have. So, here these polynomials g I of z as before. So, they have degree strictly less than d I for I range from 1 to k. So, basically you rewrite this p of z divided by c of z using this partial fractions method. So, c of z you can write it as product of these terms. Now, using partial fractions you can guarantee that this will be sum of these rational functions whose numerators will have this degree restrictions. So, that is guaranteed by partial fraction. That is something you must have learnt in high school. So, that I am going to leave it as exercise. So, if your function f satisfies this condition, then it must satisfy this condition, that is what it says. So, now as a fourth statement, one can have very explicit form of this using this binomial coefficient, the geometric series actually. So, the explicit form is given using the geometric series, can be written as follows. So, you can write f of n equal to summation p I of n alpha I power n, where I varying from 1 to k, where this p I of n is indeed a polynomial in n of degree at most di minus 1 or strictly less than di, and this is true for all I range from 1 to k. So, one can give very explicit description of f of n like what we did it for the binomial coefficient, and so that actually can be done using just by inverting this monomial, that the product of the monomial that we have here using using this geometric series. Okay, so I am going to only prove 1 and 2 and then leave rest of the things as exercise. So, one can actually use some basic linear algebra to prove this all these statements are equivalent. So, I am going to outline that proof at the end, but before that let us actually try to prove 1 and 2 straight away. So, it is easy to prove 2 implies 1. So, let us first look at that. So, the proof of 2 implies 1, and we will prove 1 implies 2. So, that will tell you that 1 and 2 are equivalent. Okay, so, let us start with Vi. So, this is those functions from n to c, and f satisfies the condition I. Okay. So, this is the set. So, basically I am collecting all the function that satisfies the condition I. So, note that the conditions I will be depending upon the coefficient that we have chosen C1 etc. CD, and of course, that C1 etc. CD determines the roots alpha 1 etc. alpha k. So, these conditions are well defined. So, now what we want to prove, suppose f satisfies the condition 2. So, that means f is in V2, then we want to prove that f is inside in V1. Okay. So, this is what the meaning of 2 implies 1. So, let us take that f of z satisfies the condition 2, which says that f of z which is f of n z power n, which is exactly given by p of z divided by c of z. Here n is varying from 0 to infinity. So, recall c of z is given by 1 plus c1 z plus etc. plus c d z power d, and then this p of z is a polynomial over complex numbers such that the degree of p of z is strictly less than d. So, this is what we have. So, now we use this to conclude that the coefficient of z power n, that is small f of n, satisfies the recurrence that we have. Okay. So, let us look at closely what this equation means. So, f of z is given by p of z divided by c of z. So, that would imply immediately that c of z times f of z is indeed given by p of z. And now, using the convolution product, we can see that looking at only the coefficients of z power d plus n for n greater than or equal to 0, we get something like this. This is summation n greater than or equal to 0 f of n plus d plus c 1 f of n plus d minus 1 plus etc. plus c d f of n, which is the coefficient of z power d plus n, and that supposed to be, this entire series is supposed to be 0, because p of z has degree up to d minus 1 only. So, from z power d plus 1, all those coefficients must be 0. That means, this entire power series must be 0. So, that is what we get from this equation. So, that means for n greater than or equal to 0, we have that f of n plus d plus c 1 f of n plus d minus 1 plus etc. plus c d f of n must be 0. So, this means f satisfies the linear recurrence of degree d that is mentioned in the condition 1. So, that means f is in V 1. So, that means f is in V 1. Okay. So, this is actually proves that V 2 is contained in V 1. So, now let us prove that V 1 is contained in V 2. So, for that let us start with f is coming from V 1. So, that means we have this recurrence f of n plus d plus C 1 f of n plus d minus 1 plus etcetera plus C d f of n is indeed 0 for all n greater than or equal to 0. So, now using this we need to actually say that when we are looking at this power series. So, that is going to be rewritten of the form P of z divided by C of z. So, recall what is f of z? F of z is given by summation f of n z power n, n is from 0 to infinity. So, this is the generating function of this counting function f. So, now what we are going to do? We are going to just rewrite f of n's using this recurrence and then we will sum. So, let us do that. So, we just basically going to take that take this recurrence, multiply with z power n plus d and then sum over n greater than or equal to 0. So, then we get summation n from 0 to infinity f of n plus d z power d plus n plus summation C 1 will come out f of n plus d minus 1 z power n plus d, again n varying from 0 to infinity plus etcetera plus summation C d will come out f of n varying from 0 to infinity z power n plus d equal to 0. Note that term like this will be equal to z power d times f of z. So, we want to rewrite everything in terms of f of z. So, that is what we are going to do, but here the sum is starting from f of d times z power d. So, for example, if you take this thing, so this is going to be equal to f of z minus summation f of j z power j ranging from 0 to d minus 1. So, this is the substitution that we need to make. So, we will make it for each one of them. So, for general k what we get? For general k we get summation f of n plus d minus k z power n plus d, where n is varying from 0 to infinity will be equal to z power k summation f of m z power m, m is varying from d minus k to infinity, which is exactly given by f of z minus this z power k should come out minus summation f of j z power j will run over from 0 to d minus k minus 1. So, know that k will run over from, so k starts with 0 here and then goes all the way to d. So, this is going from 0 to d. Okay. So, now if we substitute back this then by simplifying we get that 1 plus C 1 z plus etcetera plus C d z power d times f of z equal to p of z. What is this p of z? So, this is coming from this z power k and this summation f of g z power g. Okay. So, let me mark it in red. This term multiplied with this term is going to contribute to our p of z. So, we need to sum sum all of this. So, we need to sum all of this by multiplying by C 1 etcetera C d. So, if we multiply this with C k and then sum it over k, assuming that C naught is 1. So, then we will be doing that here with summation C k and k is running over from 0 to d. So, then you can see that this term is what contributed to this, and then whatever remains, that you call it as P of z. And this P of z you can rewrite this as summation k range from 0 to d minus 1 and f of k plus C 1 f of k minus 1 plus etcetera plus C k f of 0 times z power k. So, this is something you can check, but the most important thing is that this is a polynomial of degree at most d minus 1. So, the P of z is indeed a polynomial and the degree of P of z is going to be strictly less than d. So, here by convention we assume that f of minus 1 and so on is 0. Okay. So, that is assumed already. So, this tells that you can write f of z equal to P of z divided by that C of z that we are interested in. So, note that C of z is invertible in our formal series because it starts with the constant term 1. So, that is why this polynomial that is written here is invertible. So, one will be able to write f of z as P of z divided by C of z. So, that indeed tells us that this V 1 is indeed contained in V 2. So, this proves that V 2 is same as V 1. And similar way one can prove that V 3 is same as V 1 and V 2, and similarly one can prove that all these V i's are equal. So, let me just sketch how one can approach this using linear algebra. So, sketch of the proof using linear algebra. So, recall that V I defined to be those functions from n to c and f satisfies the condition I, and it is not difficult to prove that these V i's they are all indeed vector spaces over complex numbers. In particularly the addition of two functions will be defined by what is called pointwise addition. So, by defining addition like this and then the scalar multiplication like this. So, one can think V i's as vector spaces over complex numbers. Okay. So, that is a very important information. So, now what one can actually see, for example, if we take this recurrence f of n plus d plus C 1 f of n plus d minus 1 plus etcetera plus C d f of n equal to 0. So, this recurrence is true for all n greater than or equal to 0. That would imply that all coefficients f of n for n greater than or equal to d. So, they are all determined by the first d coefficients f of 0, f of 1 etcetera, f of d minus 1. So, that means roughly speaking we have only d freedom of choices. So, this gives us that d freedom of choices. So, that means the vector space V 1 must have dimension D. Okay. And similarly, one can actually see that the vector spaces that are defined using V 2, V 3, V 4, all of them must have dimension D. Okay. For example, V 2 is nothing but you collected all the functions from n to c such that this f of z is given by p of z divided by c of z, and the c of z is fixed, and this p of z satisfies that it is a polynomial such that the degree of p of z is indeed strictly less than d. So, that tells us that the coefficients of p of z, let us say like p naught, p 1 h z plus etcetera plus p d minus 1 z power d minus 1. So, these coefficients, they are arbitrary, and these are all the only freedom of choices that we have, because the c of z is fixed. So, that means we can take any values for this p naught etcetera p d minus 1 coming from complex numbers, and that gives us d freedom of choices, and that tells us that the dimension of this V 2 also must be D. And similar proof can be employed for this other spaces as well. So, now what happens, we already verified, which is easy to verify, that V 2 is subset of V 1, and now the dimension of V 1 and dimension of V 2, they are same, both are equal to D. That would immediately imply that V 2 must be V 1. So, this is a simple fact indeed from linear algebra. So, both of them are subspaces of some larger vector spaces, but anyway that is not important. V 1 is already a vector space, V 2 is a subspace of V 1 whose dimension is equal to dimension of V 1. So, that means V 2 must be equal to V 1. So, that actually simplifies that we do not need to check V 1 is indeed subset of V 2. So, this means it is enough to check that, for example, V 3 is subset of V 2 and V 4 is subset of V 2 or V 1. Okay. So, this is all easy to check, and one side implication will guarantee that because the dimensions are equal. So, all the sets that are in concerned here, they are all equal. So, this actually kind of gives the linear algebraic neat proof of this result, which is actually very nice. So, now I am going to end with one small application. So, we will look at this following equation, and then one can easily write down the solution. So, this is the example that I want to just demonstrate how powerful our method is. For example, if we take the recurrence, which is of the form f of n equal to 6 f of n minus 1 minus 9 f of n minus 2, with the condition that f of 0 is 0 and then f of 1 is 1. So, then what happens, you can see that the characteristic polynomial will be of the form 1 minus 6 z plus 9 z square, and the reflected polynomial is going to be exactly z square minus 6 z plus 1, which is given by z minus 3 square, and that would imply immediately that this is exactly 1 minus 3 z square. So, now what will be f of z? F of z is going to be summation this f of n z power n. So, which is given by, it is easy to verify, this is exactly z divided by 1 minus 3 z, which is exactly summation n 3 power n minus 1 z power n. Okay. So, the method is so powerful that we will be able to compute this power series very explicitly, and using that we can compute the coefficient f of n, which satisfies this recurrence. So, This demonstrate that this method is really powerful. So, this formal power series techniques will pop up in many other places, especially in algebraic combinatorics, representation theory and so on. And since this method is so powerful, it is important to learn this. Okay, I will stop here, and we will continue with inclusion, exclusion and Mobius inversion and so on in the next class. I will stop here. Thanks.